Okay, so as we were discussing, question number 3, which says to find the value of integration of the given function from the limit minus 2 to 2 and then the differentiation at 2.7. So, as I discussed earlier, that for this given function, we can find the value of the integration and differentiation by using the mathematical skills of ourselves. Okay, but this is a very simple equation. Okay, it's a polynomial. So we can do it easily. But what if the equation is very complex? It has very much higher powers of x, then it has x in the denominator with negative powers. It can have log, sine, cosine, tan inverse, and all these kind of functions. So then the equation becomes a bit complex and it takes time to get the integration or differentiation. So in that case, we can use the softwares which have the capability to do computations and that would make our task easy. So one of the software is MATLAB. So as I discussed in the earlier class also that in case of MATLAB, we can define variables, right? We can define it, the variables as numeric values, as array or as matrix, right? Like if I show you here, I can define as x is equals to 1. So x is going to take the value 1. You can see it here also. Okay, so there is one thing also that this is known as the workspace. This is the command window and this is a mat file. Okay, so for this workspace, what is there is that whatever variable we are defining in the command window, the variables are going to show up here. Okay, and here is a command window where we can promptly give the commands for the MATLAB to perform. And here is a mat file wherein we can write a series of codes or the process or the algorithms of code so that when we run this code, we can get the output instead of typing it here in the command window one by one. Okay. So here in the command window, as I gave x is equals to 1, it takes the value x is equals to 1. Likewise, I can define x as array as well, like 1, 2, 3, 4. So here x is an array. Okay, it has 4 values 1, 2, 3, 4. Apart from that, I can also define x as a matrix. By matrix, I mean 1, 2, semicolon, 3, 4. So now x is a matrix. Okay, so what is happening is that if I am writing x like this, so it is making one row with 4 columns. And if I am writing x like this, so essentially it is having 2 rows and 2 columns. So space or comma actually puts the value in the same row. And when we add semicolon after a particular value, it then takes the values after the semicolon to the next row. It is going to make a new row. For example, if I write x as 1 space 2 semicolon 3 space 4 semicolon 5 6. So this is what we get. We add 2 semicolons and we get 3 rows and 2 columns. Okay. But here I have defined x as values. Okay. Either x is having a single value, either x is varying from 1 to 4, either x is a matrix, but x is having particular values. But I want the integration or differentiation of a particular function in terms of x itself. Okay, I want that particular function as a function of x, not as numeric value. Okay, so then what am I supposed to do? So in that case, we can use the symbolic functions in MATLAB. Okay, where, just a second. Okay. Where what we can do is we can define x as a symbolic function. Here, as I have written in the PPT as well, syms. It is a command which is used to define symbolic variables in MATLAB. Syms is used to define a symbolic variable in MATLAB, which will be further used to define a symbolic function. And we can then further use it to define the symbolic function. Right. So if I use this in MATLAB, Here I have written the code, but I'll tell you step by step that how this is going to work. So I'll write syms of x. See here in the workspace, x is a 1 cross 1 symbolic variable, right? Now, since I have defined x as a symbolic variable, now I can define my function in terms of that symbolic variable, right? I'll just define f like this. See, now f, you can see here in the workspace as well, is a 1 cross 1 symbolic function f, and it is this symbolic function is defined in terms of the symbolic variable x. Okay, now since I have defined my function, I have to find two things. I have to find its integration from -2 to 2 and differentiation, and then the value of differential at 2.7. So first coming on to the integration. So integration can be done in two ways. First is the definite integral and second one is the indefinite integral, right? In case of indefinite integral, we don't put the value of the limit. Okay. So what if I want to perform an indefinite integral on f? However, the question that we have here, there we have to find the definite integral. Okay, we have the limits from -2 to 2. But in case of indefinite integral, what are we going to do? We are going to write int of function f here. See, here we got this. This is the integration of f with respect to x. This is the function. Okay, and this, okay. So what have I done is I have just given the command int of f, and I have not specified it as a variable. Okay, so in this case, it is going to take the variable ans. What happens in MATLAB by default, if we don't define a variable for a particular command, then MATLAB is going to make a variable of itself named as ans. Okay, and that particular command that we have given, the solution of that command is going to, or the output of that command is going to be stored in the MATLAB workspace as the variable ans. Okay, so that is the reason when I gave the command int of f, it made a variable of its own ans, and here is what we get, the integration. And here you can see that here in the workspace, ans is a 1 cross 1 symbolic function. After that, now if I want to find the definite integral, like if I want to find the integration of f from -2 to 2, then what do I have to do? So it can be written like this, like the third line of the code, wherein we first specify I as the variable, which is going to store the integration value. Then we write int in small brackets. We write f, comma, -2, which is the lower limit, and 2, which is the upper limit of integration. Okay. Then I press enter. And here I get the value I as 8. Correct. So, which is the same as that of the this value, which I got by the computation that I done on myself also. Okay. Now coming on to the differentiation. So, like int is a command for integration, likewise I have diff, which is the command for differentiation for a function f. Now, if I write diff of f, okay, so there is also a question that why do I want to specify a variable if the MATLAB is capable of defining a variable of itself, why do I want to define a variable? Like, why do I want to write I is equals to int of f? Why cannot I just give the command int of f? So the reason is this. See, initially I did int of f, it got stored as ans. Okay, integration. Now if I give the command diff of f, what is going to happen? Now this is the differential. And again, the default variable of MATLAB ans has taken up the value of differentiation. It has overwritten the variable ans from the integration function to the differentiation function. Okay, so that is the reason that whenever we are doing or writing some code in MATLAB, we prefer making a variable that would store the particular command that we are giving to MATLAB so that it would be helpful. Okay, so here this is the differentiation. And now what if now this is the function of differentiation, right? Whichever I'll get after differentiating f with respect to x. But I want to know that what is the value of this function at a particular value. So what am I going to do? I am going to substitute what? X. I'm going to substitute X by 2.7 in the particular function. Okay, the function that I have stored as the differentiation function. And then I'll get the value, right? So for substituting, I have the command subs, subs, which is used to substitute. Like for example, this is the function that I have defined, right? F. I want to know that what is the value of this function f for x, let us say 0. Let us say 0. So then I can write subs f comma 2. Oh, sorry, I said 0. F comma 0. So this is what I get, 0. What if I want to have the value at 1, subs of f comma 1, which is 4. And likewise, you can find similarly for differentiation, I'll get the function in terms of the variable x, and then I'm going to substitute the value of x. Like here, first I define d as a variable, diff of f. It is going to give me the function in terms of the variable x, and then I do subs. I substitute in the function d 2.7. So by default, since d is a function of only one symbolic variable, it is going to substitute what? It is going to substitute the x as 2.7. I don't have to specify that I want to give the variable x the value 2.7. Now what if my this function is maybe in terms of 2 or 3 variables xyz? Then in that case, what am I going to do? Then I have to specify that which variable is given what value so that I can get the proper solution. I'm going to write subs d comma 2.7. This is going to give me this value, which I can again compute in MATLAB itself, 21.035. Here, I get the same value by my computation itself. Okay, so this is what I get. Apart from that, when I use the command diff, it may happen that my function f is a function of y as well. Like for example, if I say that f is equals to x, okay, first I have to define 2 symbolic variables in that case, sym is x space y. What is it going to do? It is going to define 2 symbolic variables now, x and y. And then I write f is equals to x square plus y square. Okay. Now now f is a function of both x and y. Now I want to find the differentiation of f with respect to x or maybe with respect to y. Then what am I going to do? If I'm going to give diff of f, what is going to happen? To x, what did it do? By default, it differentiated f with respect to x, but I wanted the differentiation of f with respect to y. So how can I tell MATLAB that? So we use diff of f comma y. What do we do here? We perform the differentiation of f comma y with respect to y. Then we put enter. Here we got 2y. Similarly, we can do it for x as well. Like if I write x here, it is going to differentiate x with f with respect to x, right? So this is how I do the differentiation of functions. Okay, so you can just write some of the random equations on yourself. You can take examples from the internet or maybe from your maths book, like some complex functions, and then you can perform these diff and int commands on that function in order to find the integral or differentiation of that function. Okay, it will also help you understand that how these commands actually work in MATLAB, and you are going to have hands-on experience with this. Okay, then it is going to create some doubts also that with 2 variables or maybe with 10 variables, how am I going to perform? And after when you start practicing, you'll get to know that how easy it goes. Okay. Now, coming on to the PPT again. So, it is clear. Question number 3, how it is being attempted. Okay, now I guess you can use it, and when I'll share the PPT, I'll make sure that I'll just add the MATLAB command in it so that you can go through the commands by yourself. Okay, now coming on to the next question. Okay, so the next question, as it says, find the equation of motion of the spring mass damper system with forcing F sine omega t using MATLAB. Now, this is a spring mass system. It's a linear system. You all must have studied it in your mechanical vibrations course. Okay, so it's a very easy system. Since it's a linear system, you can definitely find its equation. Mm, but in order to understand that how MATLAB symbolic functions can be used in order to find the equation of motion, so we'll be using the same symbolic functions in order to derive the equation of motion. So firstly, this is a spring mass system. This is the mass M. It is attached to the fixed support by a spring K, spring with a stiffness K, and a damper with a damping constant C. And then there is this forcing of on M of F sine omega t. Right. So how many variables do I have? Like when I derive it on my own, what do? I write the mass M as M. I write the stiffness K as K, the damping as C, then I write F sine omega t like this as well. So in that case, I am not specifying the particular values. Okay, I'm finding a generalized solution in terms of M, K, C, F, and omega. Okay, and then depending upon what are the condition, how much is the mass, how much is the spring constant, and everything, I'll get the solution. Okay, so it gives me a generalized solution. So what am I going to do? I'm going to just use the Lagrange equation. Okay. So first thing that is to be done is to define the variables. What kind of variables do I want? First, I'll just clear all. Okay. Mm, like I have given the command clear all. So clear all is essentially used in order to clear all the variables that are there in the workspace. Here you can see initially there were variables like x, y, I, d, and all these. But now since I've given the command clear all these variables are cleared from the workspace. Apart from that, we also use the command clc, which is used to clear the command window. Okay, coming on to the code. Okay, so here is the code. See, what have I done here? I have used again the sims in order to define the variables m, k, c, x, f, and omega. Here you can see that I have defined x as a function of t, time, isn't it? Why have I done that? Because definitely x is varying with time. Okay, if I am going to write x like that only, what is going to happen? I can write it. Okay, but since I want the differentiation of x with respect to time, so I'm specifying, I'm telling MATLAB that okay, x is actually a function of time. So that when I say MATLAB to differentiate it, it is going to differentiate it with respect to time so that I can get x dot and x double dot. So just going for this command syms m k c x bracket t capital F omega, enter. See here the workspace. I've got these variables as symbolic functions. Okay, now what do? I want the velocity, which is x dot. X dot is what? Dx by dt, differentiation of x with respect to time. So then I can write x dot is equals to diff, differentiation of x with respect to t. So I can write it like this also, differentiation of x, enter. Now see, I have given the command x dot. I didn't tell MATLAB that x dot is a function of time. But as x, I have defined that x is a function of time. It has by on itself defined x dot as a function of time, which is given as diff of bracket x t comma t, where x dot is the differentiation of x with respect to t. Okay. Now coming on to the Lagrange equation. So what do I want in the Lagrange equation? I want L. What is L? L is kinetic energy minus potential energy. Then I want to know that what are the expressions of kinetic energy and potential energy. Right. So coming on to the kinetic energy part. Kinetic energy, we all know what it is here. Half into m x dot square. X dot is the velocity. Okay. So defining this in MATLAB, what am I going to do? Ke is equals to half 0.5 into this asterisk I am using in order to define multiplication. Okay. So multiplied by m, which I've already defined as a variable, into x dot square. So x dot I've already defined here, x dot. However, I can write it as like this also, diff of x power 2. I can use x dot, I can use diff of x. I can use diff of x comma t, whatever I want. It is going to give me the same thing. C, m into diff of x comma t, x of t comma t square by 2, half m v square. Similarly, the potential energy is defined as half into k into x square. So I'm going to define the potential energy of T as what? Half into k into x to the power 2, right? What did it give? K into x of t square divided by 2, which is half k x square. Now coming on to a very important thing, that Lagrange is defined as the kinetic energy minus potential energy. But you can see that there is a dissipation in the system because of the presence of the dashpot, isn't it? What is the dashpot going to do? It is going to dissipate the energy, right? But if it is going to dissipate the energy, where am I going to consider it? What is the energy contribution of the dashpot? So as we know that the work done, this the force applied by the dashpot or the dissipative force is not a conservative force. Is it conservative? No, it is not. Obviously not. It's a non-conservative force. So in that case, I cannot consider its contribution in the potential energy. Neither it is a inertia force. So I cannot, it does not contribute towards the kinetic energy. So it is not going to come in the kinetic energy as well. So how am I going to consider it? So as you people must have studied, so and you can recall it that in the lecture it has been taught that in case of extended Hamilton's principle, there was this Wn, which was the work done due to the non-conservative forces. Right, it was there in the extended Hamilton's principle in order to consider the contribution of the non-conservative forces into the energy equation so that we get the correct equation of motion. So this is also non-conservative force. So in the Lagrange equation, how are we going to consider it? So in case of Lagrange equation, we consider the force because of this dashpot in terms of the generalized force, right? So we have two things now that contribute as the generalized force. One is the F sine omega t, and the second one is the Cx dot, right? Cx dot is the force due to the dissipation. Okay, so here you can see that for this mass m, F sine omega t is acting in the downward direction, correct? And so if this mass is going in the downward direction, where is the this Cx dot going to take place? In which direction? Obviously, it is going to be in this direction, upward direction. That is, it is going to be in the opposite direction to that of F sine omega t. Okay, so our this force capital Q generalized force is going to be F sine omega t minus C x dot. Absolutely. Okay. So if I come on to this equation here, right? Okay, so first I'll define the Lagrange as equals to kinetic energy minus potential energy. See, here I can get it. This is x dot square m by 2, which is the kinetic energy minus k x square by 2, which is the potential energy. Next, we have to define the generalized force, which is given in this form. It's given as q into f. Q is equals to f sine omega t minus c into diff of x, which is x dot. Let us use x dot here. Here, I got the generalized force. Now, I want to apply the equation of motion. So first, let us see in this PPT that the Lagrange equation is given like this: d by dt of this differential of Lagrange with respect to x dot minus differentiation of Lagrange with respect to x, which is equals to capital Q. Now I want to write this in MATLAB. How am I going to write? I'll just not copy paste it from the code. I'll just try to write it so that you people are going to understand. So diff of first is the differentiation with respect to time of some function, which is the differentiation of L with respect to x dot. So I'll just say that there is this some function, comma, with respect to time. Now what is this function? This function is another differentiation. Is the differentiation of what? Lagrange with respect to x dot. Definitely, right? I hope this is clear. Coming on to minus differentiation of Lagrange with respect to x. I can write it as diff of L, comma, what is going to come? X, correct? And is equal to Q. Now, why am I using 2 is equal to and not 1 is equal to? The reason is that when I use 1 is equal to, what is going to happen? See here, earlier I was using 1 is equal to. What was happening? I defined a variable. Okay, I wrote that that variable is equal to this. So that variable was taking the value. The LHS was taking the value that I was giving on the right hand side. Correct? So is equal to was actually giving a variable a particular value. But in this case, what am I doing? I'm actually equating. I'm saying that the whatever is present on the LHS is equal to the RHS. Okay, I'm not replacing the LHS by the variable or function or anything that is on the RHS. I'm saying that the LHS is equal to RHS so that I can get the equation of motion, and that is the reason that I'm using 2 is equals to this. Enter. Here, I got the equation of motion. You can see m into diff of c here. This bracket, it contains x of t, which is the differentiation of x double, second differentiation of x with respect to time, which is x double dot, mx double dot plus kx is equals to f sine omega t minus of c, differentiation of x with respect to time, which is the x dot. Okay, so it gave me the same equation. Mx double dot plus cx plus kx is equals to f sine omega t, isn't it? Though you can for a linear system you can do it on yourself also. It is not a big task. But I just took this question in order to give you an understanding how can we use the symbolic functions, symbolic variables in MATLAB in order to get the equation of motion. See, this is a very simple case and that is why it looks easy. But if you have a very complex system, for example, if you want to like have the equation of motion of turbine blade or maybe of a electroactive polymer that actuates on electrical actuation, it becomes difficult. Okay, because the equations are very nonlinear, the coupling is nonlinear, it is going to have nonlinear terms in the energy, and that is why taking out the proper equation of motion becomes a difficult task. Okay, so MATLAB can help you with those tasks. Okay, now I guess this is clear to everyone that how this is happening. However, if you have any questions, you can ask. in the next class as well. Okay, I'll be happy to answer your queries. Coming on to the next question. Now, using the equation of motion obtained in the previous section, considering m is equals to 1, k is equals to 2, and c is okay. Just a second, I guess I missed the answer. Okay, here the answer is D. Okay, I'll just mark it red. Here. So if I consider m1, k2, c is equals to 1, f0 and omega 0, the system attains the equilibrium point. Okay, so it is saying that for zero forcing function, zero amplitude of the forcing function and zero frequency, the system is going to attain which equilibrium point? See, this is a very easy question. Okay, this question is something which is not going to take even seconds to answer, right? Because this is a linear system. What is going to happen if I make the forcing function amplitude and frequency both zero? What is going to happen? It becomes a spring mass dashpot system with no forcing function. Okay, so if I give it an initial perturbation, what is going to happen? It is going to oscillate, or it is going to just diminish. It is going to attain the equilibrium stretch with some time depending upon the value of C. Okay, the time would depend on C, right? But if C is present, it is anyways going to attain the equilibrium point. And what is the equilibrium point? 0, comma 0, obviously, isn't it? 0, comma 0. So this is your answer. But the question is that correct answer 0, comma 0. It is an easy task, right? You can just do it on yourself just by looking at the question. Okay. But the question arises is that what if there is a nonlinearity in the system? How are you going to know that what is the effect of the system? Right. So, and the nonlinearity is considered so that you can get the idea of how you can use MATLAB. So see, in case of a linear equation, you can just solve it, okay, by using the concepts of ordinary differential equations, and you can solve the equation to get the solution in terms of complementary function and particular integral, and then from that equation, from that closed form solution, you can get that how the system is going to behave for the particular values of the parameters m, k, c, capital F and omega, right? And for a particular time, for a set of time, whatever you want. But what if there is some nonlinearity in the system? Can you get the closed form solution? Yes, you can get the closed form solution, but the problem is that it becomes difficult. Right, in case of linear systems, it is easy to get the closed form solution. But in case of non-linear system, it becomes difficult to get the closed form solution of a differential equation. So that is why it is preferred that we use the numerical method in order to solve the nonlinear differential equation. Right. By solving through the numerical technique, we can know that for a particular initial condition and for a particular value of the parameters, how the system is going to behave for a particular set of value, for a particular value of time, depending upon the condition. Right. So what is the concept of numerical method? So I guess you people must have learned in your numerical methods course that there are various methods like the Euler method, implicit Euler method, explicit Euler method, the fourth order RK method, eighth order RK method. These are all the methods that are being used to solve the differential equations. Okay, in the like nonlinear equations by numerical method. So what do we do? Like, for example, if I want to know that what is the response of system at some t n plus 1. So in order to compute that t n plus 1, I use the value of the system, or actually the state of the system at t n. Okay, then I'm going to use the state of the system at t n, and then I'm going to compute the solution of the system at Tn plus 1, and I try that the difference between this Tn and the Tn plus 1 is very small. Okay, so that whatever assumption that I'm using is satisfied, is correct for that particular interval, right? So using the numerical scheme, we can solve. So for this given equation, if I consider some nonlinearity as beta x cube in the system, and then I want to know that how the system is going to behave for a particular set of parameter and for a particular time, for a particular initial condition, obviously. Why do I want to give, why do I have to give the initial condition? There is also a question. So as I said earlier, that in order to know that what is the behavior of the system at Tn plus 1, I need to know that what is the behavior of the system at Tn. Correct. So if I don't know what is the behavior of the system at Tn, I cannot compute Tn plus 1. Right. So T at t is equals to 0, if I know the velocity, I know the position, then I can compute whatever the trajectory of the system is for a very long period of time. But I need to know that what is the initial condition. That is why the ordinary differential equations are also known as the initial value problems when they are solved numerically. Because initial value problems, in case of we want the initial values, okay, in order to compute the further values by the numerical technique. Okay. So now this ODE45 is a built-in numerical technique in MATLAB, which is used for solving numerical differential equations. So what is ODE45 doing? Nothing. It is just computing the value of integration. Like if I give it x dot, it is going to calculate x and give it to me. Right. But in this equation, I have x double dot. I don't have x dot. I have x double dot, I have x dot, and I have x, and I want the value of x with time. What am I going to do? OD45 is giving me x out of x dot, but I have x double dot, and I want to get x. What will I do? I cannot integrate it two times, right? So what am I supposed to do? OD45, if I am going to give it x double dot, it is not going to integrate and give me x on its own. Okay, so what am I going to do? So this is a second order differential equation, isn't it? In order to get the variation of x with respect to time, I'm going to change this second order differential equations into two first order differential equation. Okay, how will I do it? Like this. See here. So see, I had two things, x dot and x double dot. Alright. Now I want to get the position x. How am I going to get the position x? If I give OD45 x dot, it is going to give me x. But I have x double dot. So what will I do? I'll first give OD45 x double dot. It is going to compute x dot from it. And then using that x dot as another input, it is going to give me x. Correct? So what am I going to do? I'm going to define a variable z. See here, as I write, z of 1 is equals to x. Okay. And z of 2 is equals to x dot. So what is happening over here is that z of 1 is equals to x. So this 1 and 2 are essentially the index. Now when I say index, what I actually mean is, see here, I'll just tell you. For example, if I define let's just clear first, clear all, CLC. Okay, now let me define a variable x as an maybe array. Let me give it some random values here. So x has one row and four columns, right? Now when I call x of 1, it gave me 7. Now when I write x of 2, it gave me 4. So what is this value that I'm giving in the bracket? It is the index. Okay. If x is an array, I can give it an index. I can say that, okay, please call this function, call this number, whichever is at this place. See, if I have a matrix, I want to know that at that particular column and that particular row, what is the value? What am I going to do? I'm call it by an index. I'll call it by specifying that particular column and that particular row. Similarly, for MATLAB, there is indexing of, in case of the arrays. So what is going to happen is this, the digit that I'm writing inside this bracket, it is going to give me whatever variable is present on that particular index of the array. All right. For example, it has only four values, right? So it is going to have only 4 index. What if I write x of 5? Will it give me some value? See what is written. Index exceeds the number of array elements. Index must not exceed 4. Okay, index cannot go more than the number of values that are present inside that particular array. So in case of matrix also, this is also applicable. Like for example, if I write x is equals to, if I want to make it a 2 cross 2 matrix, 6, 7, here. X is a 2 cross 2 matrix, 6, 7, 9, 3. So in this case, how the indexing is happening? Let us see. So if I define x of 1, it is going to give me 6, x of 2, it is going to give me 9, which means that now in case of a matrix, the indexing is going to go like this. Like it is going to first 1, 2, it is going to first go with an increasing manner in the first column, then it would go to the second column, first row and second column, and then it is going to further go in the increasing order. Like that it will go on. Okay, but in case of matrix we can also use the same concept. Like I want to know that what is on the second row, second column, so I can write x of 2 comma 2 and it is going to give me the value 3, right? So this is how indexing happens. I'll just open this code as well, which I've made for the system that I'm trying to tell you. Okay, just a second. Here, yeah. So x of 1 I am saying is x and x of 2 is x dot. So what am I doing? I'm making z as a variable. Now this variable has 2 rows. Okay. So the first row of this variable has the data or the information about x, which is the position. And the second row of this variable z is going to have all the data or idea about the data about the velocity, right? So I'm saying z of 1 is x and z of 2 is x dot. What have I done? I have changed the second order differential equation into two first order differential equation. Okay. So as I said that z of 1 is x. So how am I going to get x by OD45? If I'm going to write here, if I'm going to give it x dot, it is going to give me as x. And if I give it x double dot, it is going to give me x dot, which is in stored as z2, right? So then what will I give to MATLAB as z dot? Here, see, z dot is z of 2. Z of 2 is what? X dot. So first row of z dot is velocity. So it is going to integrate the first row and it is going to give me what? The position. It is going to give me the position values for the time that I'm going to give it as input. Okay. Coming on to the second row. Second row I've given as 1 by m. See here, for the given equation, if I don't consider for now this nonlinear term, this x double dot can be written as, these terms are going to come on this side, on the right hand side. So minus of cx dot minus of kx, it is going to come on the right hand side, and this whole divided by m, right? So this is how it becomes. Z dot is equals to, first is going to be, first is going to be z2 velocity, second is going to be acceleration. So OD45 is going to integrate the velocity to give me position, and it's going to integrate the acceleration to give me the velocity, right? So one thing that is to be understood is that I'm writing minus of c into z2. I'm not writing minus of c into x dot. Why? Because I've already defined that z of 1 is x and z of 2 is x dot. So now I don't have to write it in terms of x dot. I'll write it in terms of z. So minus c into z2, which is the velocity, and minus of k into z1, where z1 is nothing but the position, plus f sine of omega t. So I'm going to write it in MATLAB like this. Here you can see it in terms of a function. Okay, so what am I doing? I'm basically defining a function which is ODE ODE function, bracket, I'm specifying time t, capital Z, which is my variable. Then I'm defining the parameters MKCF omega W. Here I've used W. So these are the parameters whose value I have defined on the first line of the code. Right. And then I have written end. And Z dot I have defined like in the same way as I've shown in the PPT. Here also I've defined it like this. Okay. So I've defined Z dot. Okay. Now what am I doing? I first defined the function here at the end of the code, and then I'll go on the first line of the code. So I've defined the values. Here is the time, and time is like for this time. I want to compute the integral of the function for the time 0 to 20 at an interval of 0.01. Okay, and then I am defining the initial displacement as 0.5. Initial displacement, since I have explained it earlier also, it's an initial value problem. In order to compute the condition of x at tn plus 1, I need to know that what is the position or velocity of velocity of the system at tn. So that is why in order to start the simulation, I need to know that what is the position and velocity of x at time 0. Okay, so for now I specified initial displacement as 0.5 and the initial velocity as 0 here. Z naught I have defined as a like this. Then options I've kept it open as of now. Then I have t comma z, which is equals to ODE45, and it is calling first it is at the rate ODEFU, and it is calling the function that I have defined at the end of the code. Okay, after it calls the function, I am calling the time for which it is to be integrated, or time for which ODE45 is to be applied. Then I call Z0, which is the initial condition. Then I call options where here I have kept it as nothing. You can specify the relative tolerance, absolute tolerance, and all these things here in order to get uh, accurate values. Okay. Then I have called the variables or the parameters m, k, c, capital F, omega. So it is also important to understand that since in this function I have used m, c, k, f, omega like this in terms of variables, and I have not used it as numeric values. If I would have used numeric values instead of these variables, I didn't have to call it. Firstly, I didn't have to define ODE fun in terms of these values. Okay. And secondly, I didn't have to define these values on the first line of the code. Neither do I have to define it in the ODE45 also. Okay. I'm calling it because I've defined these function in terms of these variables. I've not defined it in terms of the numeric values. Okay. So this is to be taken care of when you are writing code in ODE45. Okay. So here, so this fifth line of the code is going to compute. It is going to integrate, numerically integrate this z dot in order, and it will store the time in t and the velocity and the displacement or the position in z. Okay, it is going to store it, and it is going to get stored, and it will appear in the workspace. After that, I plot the figure of time and position versus time, and the position versus velocity. So for figure 1, I call plot t comma z colon comma 1. So plot function in MATLAB, it works like plot x comma y. Okay, plot, first you are going to write in the bracket, first you're going to write the x or whatever you want on the abscissa, comma, you'll have to write whatever you want on the y or on the ordinate of the plot, x comma y. So I have called t comma z colon comma 1. Now when I'm calling colon comma 1, it means that I want only the position data. I'm plotting only the position data. Okay. So when I'm writing colon comma 1, it means that I want to plot all the position data. Okay. And when I write colon comma 2, it means that I'm selecting all the velocity data. Okay. Then I apply hold on. So why am I applying hold on? Hold on is basically to hold the image. This I'll explain when I'll go to the other question. Okay. And here I have figure 2, plot z colon comma 1 comma z colon comma 2. Here I'm plotting the position versus velocity, velocity versus position rather, and here I can go get the phase plot. So I'll just run this code and see what is going to happen. So this is as same as the question that I gave you. Okay, here, see, here is the phase plot and here is the time response. So this is how OD45 works. Now, in case you want to know that what the system is going to behave if I would consider nonlinearity, then you can add the nonlinearity as well here. You can add the z1 to the power 3 term and then you can integrate it. It makes it easier, dealing with the nonlinear equation. For the linear equation, you can go for the closed form solution since it's a much reliable way. But in case of nonlinear system, the numerical techniques is used. Okay. So going on to the PPT. So I hope this is clear. Now coming on to the next part. Okay, so I wanted to discuss this question again because I discussed it in the week one's interaction also, but due to time constraint, I was not able to discuss it in an elaborative manner. So I'll just discuss it again. So as the question says, here's the van der Pol equation. So for a van der Pol equation, if you will see that there is no forcing function present here, right? For this spring mass system, when I was simulating what was happening here, what was happening here, C was 0. Okay, I'll take some damping, let us say 1. What will happen? See what's happening. Initially it was 0.5, its position. Then it showed some oscillation diminishing, and then it went to the stable state, right? It went to the equilibrium state, 0. And here also you can see that it goes to the position 0 and velocity 0. Alright, because of the presence of damping in the system. Okay, but if there is some forcing, what is going to happen? Let us say there is this F1 and omega is also 1. What happened? It is following a periodic oscillation, isn't it? It is following a periodic oscillation, but it is having a forcing function. In case of van der Pol equation, is there any forcing function present here? No, there is no forcing function. Correct. So what is happening in this van der Pol equation? So see, the response of the system after 10 seconds as the initial condition changes from 1, 0 to 2.5, 1. What is going to happen? Let us see. So if I go to the code of the van der Pol's equation, this is the code. Okay, let me just run it. So this is the time response and this is the phase plot. You can see that it is making a periodic response, right? There is a loop, okay, not a circular but a loop, which it is a closed orbit, which is it is following with time, and it is obviously a periodic response. So what is going to happen if I change its initial condition? Initial condition is 1 comma 1. Wait, we have 1 comma 0 now, okay, and 2.5 comma 1. So 1 comma 0, this is the response. Okay, now if I want to compare it with 2.5 comma 1, so I have used hold on here so that these figures are going to be there. Okay, like for example, if I remove this hold on, I'll just show you that what is going to happen if I remove the hold on command. See, if I remove the hold on, these are the two figures, figure 1 and figure 2. You can see here. Okay, these are the two figures. Now if I want to compare these two figures, What would I prefer? I'll prefer that the figure for the other initial condition gets plotted in the same figure so that I can compare. Okay, is it the same or not? It is properly tracing the same path or not? The orbit is the same or not? Whatsoever. So I'll just run this equation. Okay, sorry, the hold on was already there. See, so here are the two plots. Now I change the initial condition. I'll just go for 1 and 0, and I'll just run it. What happened? The previous figure, it got erased and the new figures got plotted. So how will I now compare? I want the all the two figures to plot in the same plot, right? So that I can compare it. So that is why we use the hold on in plots. By applying hold on, after I use the second initial condition, I run the code. Instead of removing and then plotting the figure, the previous plot is going to stay, and in that plot only the second plot is going to get plotted with some different color, so that then I'll be able to compare it. As I applied hold on, the code was the code gave this. Now I'll change the initial condition to 2.5, 1, and then I'll again run the code. See, the response got plotted in the same figure. See what's happening. See here. So the response, if you see in the phase plot, for both the initial condition, the initial plot is different. Okay. But if you see the response after some time, it is following the same path. The phase plot is the same for both the cases. It is following the same closed loop, isn't it? So what is essentially happening? In case of a spring mass system and there was a damper present, what was the damper doing? It was reducing the velocity, right? It was plus c x dot. If the x dot is positive, it is going to like pull it from the positive velocity and it is going to try to make it come to 0. If the velocity is negative, then in that case also the damping is going to pull the velocity and make it come to 0. In case of van der Pol equation, this is not the case. Okay, the damping equation, if you see here 1.5 into 1 minus v square into v dot. Now this 1 minus v square, what is this doing? Now see, if v square is greater than 1, what is going to happen? Here in the bracket, it is going to be negative, 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 positive. What is going to happen? It is going to create a positive effect, right? Positive effect means that here it is going to be plus. If the velocity is positive, it is going to make it to 0. If the velocity is negative, then also it will try. But if the v square is less than 1, so what is going to happen? Here it will be minus only, because it is going to be positive, it is going to be minus. So in this case, if our velocity is positive, what is it going to do? It will not pull the velocity to come to 0, it will make it more. And if the velocity is negative, then what is it going to do? Now also it is not going to make the velocity to come to 0, it is going to increase it. It is creating a opposite effect to that of the damper, no? So depending upon this V, what is going to happen, the damping effect is going to change, right? So because of this change in the damping effect, what is happening? It is actually forcing what? Forcing the system to follow a particular path. So if I am giving it an initial condition which is outside of that phase plot, here you can see, right? I'll just explain you with this figure. If I'm giving it an initial condition which is outside of this closed path, what is happening? The equation of motion is actually trying to make this system come and follow this path. It is forcefully making this system to follow this closed trajectory. And what if I'm giving it, so what is it doing? It is actually reducing. Here it is reducing. And what is happening here? If I'm giving it an initial condition which lies inside of that closed trajectory, it is actually forcing this system to go out of this inside of the trajectory and go out and follow this trajectory. Isn't it? This is what is happening to the system. So the van der Pol equation, though not having forcing function, is showing a periodic oscillation, isn't it? And we are calling that this as a limit cycle because it is always following this particular closed trajectory. It is not going outside of this trajectory. It does not depend on the initial condition. If the initial condition is outside of this trajectory, it is then also coming to follow this trajectory. If it is inside of this, then also it is going to follow the trajectory. This is not in case of a spring mass system, isn't it? Like for the spring mass system, where did it go? See here, what have I taken? I have taken the initial displacement at 0.5, isn't it? I'll just run it. Okay, wait, I'll just change. Let me just make the damping also 0, forcing also 0, and omega also 0. It is going to follow a close. We know that it is going to show periodic. This is the periodic oscillation. Alright. What if now I want to change the initial condition? I'll say outside. Sorry. So I'll just make it 1.5. See what happened. As I increase the initial displacement, the loop changes itself, which means that depending on the initial condition, the amplitude of oscillation is going to change. If my initial condition is changing, then my amplitude of oscillation is changing. I can change this 0.5. It was initially 0.5, then I make it 1.5. I'll just make it 0.1. I'll again run this section. What is going to happen? See this yellow plot, what happened? Now it is following this trajectory. So this phase plot is changing. The amplitude of this periodic oscillation that the system is showing, it is changing depending upon the initial displacement that I am giving to it. Likewise, if I change the initial velocity also, it is going to follow different paths, right? So this is a periodic orbit. We say that it is following a periodic orbit. The solution is periodic. But in case of van der Pol equation, this is not what is happening. With the change of initial condition, the phase plot is not changing. Though there is some initial changes, but after a certain time, it is again and again following the same loop, isn't it? See here, for 2.5 comma 1, it is following this trajectory. I'll just change it to 1.5. Again, same. I'll just do it 0.5, 0.5. See, same. I'll make it 0.2, 0.2, same. What is happening? What is essentially happening in this system? It is always following the same closed trajectory, whatever be the initial condition. And this shows the existence of limit cycles. Though it is following a periodic orbit, but it is the limit cycle. This periodic orbit is a limit cycle. We say that it's a limit cycle because with the change of initial condition, the closed trajectory that it is following is not changing. It is the same. Okay, so this shows the existence of limit cycles. Right. So in the nature, maximum whatever the natural things are, they follow the limit cycle. Okay, they are independent of the initial condition, the trajectory is going to be the same for a particular parameter. However, this trajectory is going to change if I'm going to change mu, right? If I'm going to change mu, no, if I make it maybe 2.5, then this is going to change. Then you see the trajectory changed itself. But similar to the initial argument also, if I change the initial condition, we make it 1, okay, it's still going to follow the trajectory. It is independent of the initial condition. And the initial condition is not going to hamper the limit cycle. It is always going to follow the same periodic loop, and that is how a van der Pol equation is different from has a different behavior than that of a Duffing system, Duffing oscillator system, right? So here I guess it is clear for you people that what has happened is that is why remains the same. In the phase plot, it is going to remain the same despite of the initial condition because of the limit cycle, right? So this is the code, and I hope that the every line of this code is clear to you all, because I've explained it in case of the spring mass damper system also. So yeah, now I'll just take up this another question which is related to the Lorenz equation. So the first thing about the Lorenz equation, if you'll see the equation of motion, is that the Lorenz system is a three-dimensional system, isn't it? Yes, there are three uh, differential with respect to time: x dot, y dot, and z dot. The first equation I have x dot, and these three equations are coupled obviously, and these are nonlinear. You can see here x is multiplied by z, x is multiplied by y. So this is a nonlinear equation. Okay, so what you can see, there are three equations. So in case of ODE for 5, I'll have to put on three equations, and then I'll have to solve it in order to know that what is the response of the system for the three initial conditions. So you can see however, how many first order differential equation we are giving to ODE for 5. The initial condition is also going to have the same dimension. If then there were two differential equations, two first order differential equations, there were two initial conditions. Here we have three first order differential equations, so we are going to have three initial conditions, right? So I'll just show you the code. Just a second. See, here I have defined z dot like this. Here I have defined three rows. First row, second row, and this is the third row. Why have I done this? Because I have three this first order differential equations, isn't it? So coming on to that, how the system is going to behave, right? So I guess you're clear with the code. See, I have sigma into z2, where z2 is what? Y minus z1, which is x. Compare it. It is 10 y minus x. 10 I have taken it as a variable, which is sigma. Sigma I have defined as, see here, 10. Right. Then I have z1, which is x, into rho minus z3, rho minus z. See here, 28 into x. I have z1 into rho minus z3. Okay, so I have done it like this. I have taken x as common, and then I have this 28 minus z. Z is here z3. Okay, minus of z2, which is y. Y. Then I have z dot, which is xy dot, which is z1 into z2, x into y minus beta into z3. And I have beta as 8 by 3 and into z. Okay, so this is my equation. Now I have defined sigma as 10, rho as 28, and beta as 8 by 3. Then I have defined time as Okay, I'll just first define the time 10 till 10. Okay, then I want to know that what is the system behavior for the initial displacement 1, 1, and 1. So I'll just run this code. Okay, so the behavior I get it like this. Okay, let us take some more time, 20 maybe. The system is showing this kind of a behavior, right? So, okay, wait, I'll just mark the labels so that it will be easier to understand. Let me just give X label. So label, X label and Y label are essentially given the command in order to name the abscissa and ordinate, right? Capital X, Y label is Y. I'll just run the code. See here. This is X with respect to time and this is Y comma Y versus X plot. You can see with time how it is changing. So looking at this behavior, what I know is that this is not a fixed point behavior and this is not a periodic behavior. I have two options left now, which is quasi-periodic and chaotic. So what is this? How am I going to know whether it is chaotic or quasi-periodic? So there comes a concept of the butterfly effect. Okay, so the butterfly effect essentially says that if a butterfly flaps its wing, okay, so if you stand beside a butterfly and if it is flapping its wing, can you feel anything? You're not going to feel anything, right? You cannot even listen to the flapping noise. Why is it so? Because because of its flapping, the change in the velocity or the state of the air around that is very small. It is very insignificant. Okay, you can neglect it. It is so small you cannot feel it. But it is said that even if a butterfly is flapping its wing at a position, then it may happen that that flapping of wing may cause tornado at some position on this earth. Or maybe it can decelerate a tornado at some position. You know, that flapping of wind keeps on increasing in such a tremendous way that is going to affect at a large at a greater distance. It is going to create such a large variation in the atmosphere over there, in the environment over there, and you're not able to even feel that the butterfly is flapping their wing. So this is known as the butterfly effect, and this is from where the concept of chaotic system or the chaotic behavior comes from. So which essentially means that the small change in the initial state of the system, a very small, I would say insignificant change in the initial state of the system can cause tremendous change in the system behavior at a long time. Okay, so now if I know this behavior of chaotic vibration, so I can test it here. I'll just change the initial condition by a very small amount. Like here, I'll just add a 1 here. And I'll again run section. See here, there is a hold on, so it is going to plot on that particular figure itself. What happened? Well, the behavior is same, but it is for a very small interval, isn't it? Let me just do one thing. I'll just increase the time. Maybe to 50. Okay, fine. Let's just take 100. Now this is the phase plot. This is the time response. I'll just change the initial condition. I'll just remove this one from here. I'll just again run it. What happened? Let us just concentrate on its time response. See, till this time almost let us say till here. 27.03, the system behavior was exactly the same. This small change in the initial condition was not able to differentiate the behavior. The behavior was same. But after this point, if I see the change in the system behavior is very tremendous. Can you see that how much change in the behavior you can see? Like for example, if I consider this, I'll just zoom a small part here, let us say what is happening. See, at this particular time, and let us say some 29.2 time, what is happening? I assumed that the system would be at its high state. The system's position should be positive, isn't it? Its position should be positive. I expected the system to behave at this particular timestamp. But what is happening? The behavior is absolutely opposite. The system is as is having a negative position, that too as a very high value. So what is happening? Even a small change in the initial condition, you can see where was the change? It was on the 1, 2, 3, 4, 5, sixth decimal place. I added a 1. Isn't it? 10 to the power minus 6 was the variation in the initial state, which resulted in such tremendous change in the system behavior, isn't it? So, if there is so much tremendous change in the system behavior, then how am I going to design the system? Isn't it? Because by manual error, by machine error, by calculation error, due to some accuracy, it may happen that this small error can happen. But the system behavior is going to be absolutely opposite. Then if I'm designing the system at this particular timestamp, the system is supposed to be having a positive position, but it is having a negative position. So its design should be done in a very precise manner in order to counter the chaotic vibrations, isn't it? And that is why in physical system the chaotic vibrations are essentially avoided. But there is one thing that is to be noticed about the chaotic vibrations, which is that these chaotic vibrations are actually bounded, isn't it? They are bounded between the values minus 20 to 20, isn't it? It is always in between minus 20 to 20. It is never going to an infinite value, which is a very nice thing about chaos. It can never go to a infinite value. Okay, so I hope this is clear, and by this you can see that the system behavior is chaotic. So for this is the correct answer. The system behavior is chaotic. Okay, so when I share the PPT, I'll add the code in these PPT and then I'll share it, and then you can go through those codes, and I'd recommend that you should practice these codes, writing the code, and then using those code, using the algorithm in order to compute some other ODEs, so that it would help you to get hands-on experience on MATLAB, and it will be easier for you to solve the assignments as well. Okay, so that is it. If you have any questions, you can definitely ask in the next lecture, and I'll be very happy to answer your queries. Okay, so this was it for today. Thank you so much.